All right, we're starting Unit 3 today. And Unit 3 is about energy. It is also probably some of the more complicated reading that you will get into this year. Next unit, the material gets a little bit dense, so push through it. I have confidence that you can do it. I have not graded all the tests yet, and I will get them back soon. And at the end of this class, or towards the end of this class, I want to make sure that everybody's had a chance to send me the video project. In some cases, you may be working with someone in a different class, and they have it, and they'll send it, which is fine. I just want to make sure we're on the same page with all that. We also have a fun sheet today. So after I get done talking, I didn't print it up and make copies. I'm just going to have you go onto the coursework page. And it's just the front, really, of the fun sheet that I want to look at. And we can even pair up, or you can work on your own to go through it and just give what you think is your best answer. And then we'll go over those next class. This is the only class we have this week. I will see you on Monday. And we will continue to push through, and we have a couple of lab opportunities this time around. And hopefully by the end of this weekend, I will have all the tests graded, all the projects graded, and be caught up with my life. So, the beginning of chapter 8, which you were supposed to read for today, those first 3 sections, is about energy in general. It's almost more of a physics lesson, and that's really what we're going to look at today. We're going to throw some biology stuff in there, but a lot of this you probably saw in physics or even chemistry, but probably more like AP chemistry when it comes to some of the discussions of enthalpy and free energy that we'll look at. But I wanted to start with this little story that the book tells about these bioluminescent click beetle larvae that are found in some termite hills. I don't remember where exactly this is. But your book talks about how this is a process that releases energy. And I like this diagram because it just kind of goes through and shows the general pathway of energy for all living things, basically in reference to any procedure process that you undergo. And it all starts with what? The sun. The sun. That is going to be the ultimate source of energy for almost every process. There are some living things that actually, and this is usually like deep sea organisms that rely on what energy source that isn't the sun? Yeah, geothermal heat vents, that's right. So the core of the earth has so much heat in it that if you go deep enough, you do start finding life that obtains its energy from there. But unless you're eating some kind of weird, like sulfury worm at the bottom of the ocean, most of your energy probably can be traced back to the sun. And as we will discuss this unit, autotrophs, like plants, take sunlight and convert it from one form into another form. Primarily what sugar? Glucose. That's right. So plants are really good at converting the solar energy from the sun to a chemical form of energy known as glucose. Anything that eats, and the plants themselves, I wouldn't say they are eating, but they use that glucose. And when you eat, you are going to use that glucose and other organic molecules. And you're going to convert those chemicals into your form or into forms of energy that let you do things. So there's just kind of a general pathway that again leads back to the sun. Everything leads back to the sun. Now, at every step of the way, whether it's plants absorbing sunlight and making sugar, or animals that are eating those plants, or animals that eat the plants, at every step of the way, you lose energy from the process, from this general chain of steps in the form of heat, typically. All right? So they make this point, like heat is given off at every point along the way. And what's really nice about the diagram here and how they organize it is, we'll talk about the first and second law of thermodynamics in a second, but here we see as energy changes form, the first law of thermodynamics, and at each step, at each transformation, you are losing energy in the form of heat from the system, and that is what the second law of thermodynamics states. So I want to go through just some general terms. I know there's a lot of words written up here, and you don't have to write any of them down because you have these slides. But the idea of metabolism, catabolism, and anabolism, or catabolic and anabolic pathways. So metabolism in general is just a word we use, and again, it's just defined right here. But metabolism is a general term for the chemical processes that you see happen in living things. Now, the reactions that make up your metabolic activity come in two general forms. You are breaking some things down, and in other cases, you are building things up. So this idea of a catabolic pathway is you tearing something apart, really typically to get at that energy. So when you're breaking something down, you're commonly going to get energy from that process that can be used for something to happen. And that's what we do, say, with glucose, or digestion in general. You are breaking your food down, and that is a catabolic pathway. The anabolic pathway is going to be where you take that energy and you build you. You are creating the chemicals, creating the complexity, creating the organization that makes you an organism. All right? So, tearing apart versus building up. What's a way that you can remember, this catabolic as being a tearing apart or breaking down? Any simple way to remember that? To keep these terms straight? I have a weird way. Cats. What do cats do? They're always knocking things over and tearing stuff up. Yeah. So that's kind of, the cat there helps me remember that's the one where you're breaking things apart. And you may have heard the term like anabolic steroids. It's a term that you hear occasionally with like professional sports, steroid-based drugs that help people put on more muscle mass, and they call them anabolic steroids. These are steroids that help build up muscle mass. That's the idea of anabolic. Okay, so quickly, when I say energy, I mean a lot of different possible things. All right, so as it says here, energy exists in various forms. Your book goes into a lot of those. I'm not going to stand up here and define every form. Most of them you probably know. But I do want you to keep in mind that energy is a very vague term that basically is just a measure of capacity to get something done. That's what energy is. Energy is just the capacity or the ability to do work. And that's it. So whatever form that takes, whatever form that capacity to do work takes, is just going to be a form of energy. And you can change from one form of energy to the next, as we see in the laws of thermodynamics. Now there's two laws of thermodynamics. You are probably familiar with them, along with a lot of this other stuff. And the first law of thermodynamics is just the idea that there's no magic. Okay? You cannot make things disappear, and you cannot make things appear into or out of nothing. So you can't create or destroy energy. You've probably heard that idea before, and that is all we're saying with the first law of thermodynamics. Now, it gets a little weirder than that if you actually go deep into physics. There does seem to be, at a very small scale, matter and energy that leaves the universe and appears into the universe, but it actually happens at a rate that creates kind of like a net balance. So you are not ever going to take nothing and make something out of it, or take something and turn it into absolutely nothing. Matter and energy cannot be created or destroyed. First law. Pretty basic idea that you've probably heard before. And it comes up a little bit, mainly in this idea of not so much matter can't be created or destroyed, but the idea that it can be transformed from one form into another. Sunlight, sugar, work that can be done when you eat that sugar. And I know on some of these I'm moving a little fast, but I promised myself I wouldn't spend the entire class talking about this stuff. And I could, because we can get into a lot of different ideas here. The second law of thermodynamics is my favorite law of the two. It's my favorite law of thermodynamics. And the idea of the second law of thermodynamics is basically that we're headed towards chaos and disorder, and there's nothing we can do about it. That's kind of the bleak definition of it. But essentially, as it says here, every time you have some kind of energy transformation, anytime energy is turning from one form into another, you're going to lose some of that energy in the form of heat. It's all turning into heat. And we have not figured out how to reverse that process. Now, while what this law states is that everything is leading towards a more disordered state, we're always pushing towards chaos. The universe is becoming more and more disordered and less friendly towards things like us that need usable forms of energy. Every second, the universe becomes more disordered. But that doesn't mean we can't create order. You can still build a house of cards, or muscle mass, or brain tissue when you're younger. You can still create order and organization. But what do you need to do to build that order? You need energy and energy transformations in which you end up creating typically more disorder as a whole. So as a group, we could build a house or a building. We could build something nice and ordered. But what would we all need to do? What if we took the next year and we just went out in the woods and built a log cabin? What would we need? Every day, probably 3 times a day. Yeah, you need to eat. You need to eat food. Food is a very organized structure. And you are going to tear that down so that you can get the energy to keep working. And as a general rule with the second law of thermodynamics, no matter how organized and awesome of a log cabin we spent the year building, the energy we consumed is probably going to result in more disorder being created in the universe than the order of the cabin we built. But thankfully, we have an enormous hydrogen fuel cell 90 million miles away that gets enough energy to the earth that we have access to that food. And we can create this organization. But in the long term, even the sun is, kind of losing its order, even though it's a big ball of chaos. Okay, so that takes us to kind of the focus of today, which is the idea of spontaneous versus a non-spontaneous process. A spontaneous process, as the word indicates, is going to be a process that it might be slow or it might be fast, but it's a process that will happen without energy, a net energy input. And we're going to learn today, in general, what kind of process is going to be spontaneous and will occur naturally, and what kind of process is not spontaneous and you are going to have to put some energy into it to make the process happen. And then the rest of the unit is basically how we use spontaneous processes to make non-spontaneous ones happen. And that's what all the cellular respiration and photosynthesis stuff we're going to talk about over the next few chapters will be. Now, you might see some words up here like entropy that you might be somewhat familiar with. But basically, the universe likes disorder and chaos. And it doesn't like you building things and creating organization. It kind of doesn't like you. I hate to tell you that this morning, but the universe kind of doesn't like you. You are organized, and the universe is not a fan of that. And so what we find is this idea of entropy becomes fairly important, because entropy is a measure of chaos. It's a measure of disorder. And the universe likes entropy being very high. It likes a high level of chaos. And what we're trying to do as a living thing is fight that entropy, bring the entropy down, and create some order and organization, which is what the word organism means. So we're going to talk about how entropy and a few other factors play into this process. Now, to determine whether the universe is going to just kind of let something happen, or whether you need to add energy to force it to happen, against the universe's will, we have this concept of free energy. Specifically, it's called Gibbs free energy, named after the guy that developed this concept. And we use this delta G to refer to kind of what the free energy of a system is doing. And that is going to tell us, and you can calculate it. The next slide, we're going to look at an equation. Don't get scared. We're not going to do many or any calculations, but we are going to talk about the equation and what it means and how it would be used. But we're going to look at this variable delta G that indicates to us where the free energy is going. Is it going into or out of the system? And what factors are involved. So here's the equation. If you have any questions, let me know. I don't mind stopping and answering them. Everybody seems very quiet after a 4-hour PSAT/SAT / maybe a free day if you were a senior and didn't take it. So this is the equation I want us to look at. Now, number one, if you're not a math person, I don't want all the triangles scaring you. Basically, we are looking at this idea of free energy, and we're just going to talk about how there are three things that are related or taken into consideration when you talk about free energy and how easily a process may or may not happen. And one of them, temperature here, is probably the least important for our discussion today. So we're really just going to look at delta H and delta S. Now I got a few things written on the board that I am going to have you write down just so you can kind of help to keep it straight in your head. And on this slide they have listed out the definitions for the different symbols, free energy, and then this idea of enthalpy, which I'm going to try to simplify for you, which is delta H. And then we're simply subtracting the product of temperature and then a measure of order or disorder called entropy. So while it might look confusing, you're asking yourself, really, what is this number doing? What is this number doing? And how would that affect the free energy of a reaction? In fact, this is a good time to look at a few of these ideas here. And unfortunately, you may not be able to read this on the video if you look at it later. But looking at delta H real quick. Let's start there. What I'm concerned with is not so much us plugging in actual numbers, but considering what would happen when some of these variables are just a positive versus a negative value. That's what we're looking at. So delta H, this value right here, can either be positive or negative. Okay? And I didn't feel like your book did a fantastic job of talking about delta H, which is called enthalpy, which I know is very similar to the word entropy, so I don't want anybody to confuse them. But essentially, and these are terms you may or may not be familiar with, but you're probably familiar with, or at least the idea won't be too weird. If you have a reaction or a process happen in the universe, And the delta H for that process is positive. What that essentially means is that heat is being absorbed. You're sucking up heat. And we refer to that process of absorbing heat as an endothermic process. Have you heard the word endothermic before? Maybe a little bit. In AP chemistry, you definitely hear it. In regular chemistry, it's kind of a, it's a term used to describe basically whether the temperature is going up or down when you have a reaction occur in a beaker. You may not have talked about it very much. But essentially, this endothermic just means absorbing heat. And that is going to be designated as a positive delta H value. That a system is gaining heat. Now, the universe doesn't like that. The universe does not like you soaking up heat. Because the universe wants all the heat to be spread out in a very useless and chaotic way. So what the universe likes, I'm going to draw a little pink heart here. The universe loves exothermic events, where you have a negative delta H and heat is being lost. This means you're losing heat. What are you doing right now? Which one? Are you absorbing heat or are you giving off heat?
Giving off.
Yeah, you are radiating heat. And the universe is good with that, and it's part of the deal we make with the universe. We keep our organization, but in the process of doing that, there's a lot of exothermic events occurring in our body, and that heat is being lost. So a lot of the food you eat is converted into just you heating the air around you, which is pretty useless. Okay? That's not why you eat food, but a lot of the food you eat goes into that. And the universe likes that. So the universe likes for this value to be negative right here. All right? So delta H being negative, that is something the universe is A-okay with. So we're going to kind of ignore temperature. Usually in biology, you would just have some kind of standard or typical temperature that some reaction is going to happen at, and as you move away, that reaction may not happen. I mean, we're all somewhere in the 90s or Fahrenheit or 30s Celsius as a body temperature, and there's not a huge change in our range of temperatures, and that's true for many organisms. And so temperature we can actually kind of skip over when we talk about biological concepts to some extent. So for simplicity's sake, we're going to skip it over. But this delta S is important because we are subtracting it from our delta H. Okay? Delta S is entropy, and it can be positive or negative. And here it gets a little bit weird. Or it's easier to flip it around in your head and say something that's actually backwards. When you have positive values for delta S, that means you are, as you would expect from a positive value, increasing the entropy, increasing the disorder, which is basically something that we would consider chaotic or disorganized. Again, diffusion. The universe really likes things just spreading out. You can have a nice, beautiful sugar crystal. And the universe just loves taking that beautiful crystalline structure and just particle by particle spreading it around in a beaker of water. So when you increase disorder, which is a positive value, the universe is very happy, loves it, loves positive delta H. If you are creating chaos and disorder, the universe is working with you. So on the flip side, and this is where it gets a little bit weird, a negative delta S, negative entropy, means you are decreasing disorder. But we don't really say it like that. You don't, like in everyday language, you don't say, oh, I undirtied my room. I decreased the disorganization in my room. No, you just say I organized or cleaned it or something like that. So decreasing disorder, that is order. So we are constantly, having the human form and building the complex structures that we need to build to make ourselves work, we are decreasing disorder when we do that. We are creating a lot of order. And so we are reducing entropy. We're reducing the chaos. And the universe does not like that. So when you look at these two values, what the universe likes is negative delta H and a positive delta S. And that's kind of just of all the stuff, and I still have to talk for about 10 more minutes about some of the other slides to get through this. But of all the things you take away from this idea of spontaneous, not spontaneous reactions and how easily something happens and how much the universe may cooperate or fight against you, a negative delta H, where you're losing heat, and a positive delta S, where you're creating disorder, those two things are what the universe loves. And what kind of value does that give you? If this is negative and then you subtract a positive number from it, it's a really negative delta G. And that's why I wrote this part right here. A negative delta G value for a reaction, or any process, is going to be a spontaneous reaction. We actually call it or use negative because in these reactions, free energy, this delta G, free energy is lost or given away from a system. And this is a term your book will use, exergonic, where your energy is exiting the system. And those processes are spontaneous processes that will happen without you working to make them happen. They're spontaneous. So that is the main point of looking at this equation and the main point I want you to understand about it. And of course, if you have a positive value here, where a lot of heat and energy is being absorbed, and you subtract a negative value, subtracting a negative value is like adding that positive number to it. To make this positive, you are going to have to decrease disorder. You have to get a lot of order, and that is not spontaneous. And what we find in biology is that to make non-spontaneous things happen, like creating an organized human form with all its organized systems, to make that happen, you've got to make a trade with the universe. You have to say, okay, look, let me have a heart that beats rhythmically and supplies nutrients and oxygen to all these complex structures. And in return, I will tear things down, typically through eating and digestion, and constantly radiating all your heat. Okay, so we'll look at this again in just a second. That's basically on this slide everything I just said. Negative delta G is going to result in spontaneous things. If delta G is positive, it's not spontaneous, and you're going to have to do work to make it happen. And then these terms, exergonic and endergonic, which I had written on the board, are basically a way of referencing the spontaneity or non-spontaneous nature of a reaction. They're usually used for naming reactions. But what I really want, and I don't think this is in your book. This is a chart worth looking at. You could write it down. It wouldn't take a whole lot of time. But you also have it. But I would definitely try to be able to look at this and understand why something might happen without work being used to make it happen, and why something will not happen unless you put work and effort and energy into it. And this is basically, and I wrote the equation up here so that you could see this while looking at the equation. It's basically what we just did. Negative delta H with a positive increased amount of chaos or entropy. That's going to be when you have spontaneous reactions. But if you're absorbing heat and you're decreasing chaos, the universe does not like that, and it's not going to happen unless you put the work, effort, and energy into it. And then there's kind of these weird ones where like you're kind of doing one thing the universe likes, you're kind of doing something the universe doesn't like, and that's actually when temperature comes into effect. But we're not really going to do the calculations, and I will just show you the values, and it's going to either be positive or negative delta G. So, I'll leave that up there just for a second. I have a few examples to give of this, and I think we have like 3 more slides to look at, but they're all diagrams. So here we see kind of a different representation of something that's exergonic or spontaneous versus something that is not spontaneous. And your book does a good job of giving some kind of everyday examples, like diving off a diving board. If you imagine that you're on a diving board, you can just fall off. Okay? And when you're falling, you're actually losing a lot of the potential energy that you had. And when you hit the water, you're at a lower state and that energy is gone. You've spent that energy out. Now, once you're in the water, what do you have to do to get back on the diving board? Yeah, you're going to have to either reach up and grab it and do a pull-up and climb back on it, or swim to the edge of the pool, walk, step back up onto the diving board. Once you're in the water, there's going to be an energy requirement for you to get on the diving board. So basically, you can fall really easily, and the universe loves it when you fall down, or you need to put work and effort into getting back up. And it's crazy how, I mean, you can take these kind of everyday examples, and it's how all sorts of reactions and everything in the universe works. The analogies really work for basically the same reasons. So I would probably look back over this unit to look at some of those diagrams. This is not as easy of a diagram to kind of process, but again, in AP Bio, something that is done a lot is a complex looking graphic is given, and you have to kind of simplify it and explain what's going on. So here's how we actually use the numbers. Here we have this reaction where you have smaller, simpler structures that are going to combine to make a more complex structure. Does the universe like that? To take small little pieces and build them into something organized? No. The universe doesn't like that. And if you do all the thermodynamic work and calculations, what you find is the delta G, the free energy change for this reaction, is positive. The universe doesn't like positive delta G. This is not a reaction that the universe is going to just let happen. But to get this to happen in your body, we can use what? With energy. ATP in the form of energy. All right? So what ends up happening is, here's our smaller pieces we're trying to build into a more complex organized structure. But to make that happen, we make a trade with the universe. We take a more complex structure, ATP, and we let it break down. So we let our ATP break down into simpler, less organized structures, and the universe then allows us to take less organized structures and build them up. So if you look at one reaction, this first reaction, it's got a positive delta G. And if you look at the change of ATP into ADP and phosphate groups, if you do the calculations, you get a negative, a more negative, a larger magnitude number that is negative. And in the end, a little positive and a lot of negative gives you an overall change in free energy that's negative, which the universe likes, and it thus kind of makes this a spontaneous reaction that will happen. So I just want you to keep that in mind. To build things up in your body, which is against the will of the universe, you have to make a trade with the universe where you break things down. And honestly, you're always losing in the deal, because this is probably much more serious. It's a bigger number, just negative. This is probably you creating much more disorder in the overall universe than the order you're building. But it's all we got, because it's a law of thermodynamics that we're fighting here. And then finally, thank you for your patience, we are going to see this over and over and over this year. And this is basically what this unit is about. How do you get energy into ADP to convert to ATP so that we can store some energy? And then how is that ATP then converted back into a less organized form so that we can get energy to organize ourselves and to create order? So it's this constant cycle where you're creating some disorder to make some order so you can create disorder to make order. The problem is, every time you make that trade with the universe wins. You have a trade deficit with the universe, where you're constantly, after the deal is done, there's more disorder, even if you yourself are more ordered. But thankfully, we have the sun that's got at least another 1 to 2 billion years left in it, just flooding us with energy that we can use to create that order. Thank you for sitting here the whole time and listening to that. It's probably a little bit brutal. We do have a lot to cover. Your test is like the first Friday of November, which is just a few weeks away. And we've got 3 chapters, 2.5 more chapters to get through. There is a fun sheet or worksheet on your coursework page called like Free Energy Fun Sheet. Based on what you've seen today, I just want you to try to fill out the chart on the front. They basically ask you which one you think is spontaneous or not spontaneous. You're basically trying to figure out which one of these 2 things does the universe love and which one does the universe hate. And you can look at that now. And next class we'll go through and talk through all the answers at some point. And I also need to make sure that your video is going to be gotten to me. I know today is the due date, but I'm going to be honest with you. It's been a crazy last week for me and for many of you. And I will work with you on at least getting the video. Some people are having trouble sending it to me or sending it to each other so they can work on it. So what I'd like to do now is have you either look at the front of that worksheet, do your best, and we'll talk about the answers later, and or make sure I got the video and I'll sit down to double check my email, or you can airdrop it to me. So, that's it. Go ahead and stop there.